Hi Physics 2 team. I wanted to point out before I switch over to my Smart Notebook that your notes start with how to use a multimeter. And there's a video there for you on how to do this that's not made by me, but I'd still like you to try and finish these notes. So page 1 of your notes comes from that 8-minute video. You'll want to go back and use it. It should have been first. It should have been posted just before our video. A multimeter is a multimeter. The one that's in that video is actually the one that we have in lab, which is why I chose the one that I chose. The guy does a really good job walking you through it, and sometimes it's nice to hear something from somebody else. So you guys are going to start with that. When we switch over here, the how to analyze a circuit is complete for you guys. So there's nothing to add. This is just the process that we're going to work our way through in the next several videos. So I wanted to have it written down in one place for the people who like to read and process things, but we're not going to start with our notes there either because there's nothing really to add. We're going to start our notes with talking about Kirchhoff. So at that, I'm going to switch over here quickly to Kirchhoff's Junction Law. So what you should notice is that I took the lecture notes that we had and I dumped them in little tiny chunks onto different pages. So you guys have 7 pages of notes and I have 14, and that's okay. That just allows me a little bit more space and flexibility to make my screen bigger because, as you know, when I'm writing on the screen to do a lecture for you guys, I have to write a little bit bigger to get things to work out. All right, so we're going to talk about Kirchhoff for a minute because he made a couple pretty good fundamental things for us. Well, in flipping over my screen to tablet mode, I accidentally turned off the computer and it left it where it was. Super cool with that. Now we're going to start talking about Gustav Kirchhoff. So, the guy was German. He was a physicist. He lived from 1824 to 1887. So, around about 150 years ago. Just for some perspective for you. But as a scientist, he was wicked cool. If you ever need to study a scientist, he's your guy. He wrote things involving circuits. He studied spectroscopy. He actually wrote the initial papers on blackbody radiation in 1862. He had students that included Mendeleev, Max Planck, and Ernest Schroeder, which are pretty cool. Schroeder. Okay. He discovered cesium and he discovered rubidium. So the guy's just so cool. But all we're really interested in right now is the Kirchhoff's Junction Law. So here we go. Kirchhoff's Junction Law, if I grab a pen, says that the sum of the current that we put in has to equal the sum of the current that we get out. That's the law. So, what does that mean in a drawing form? Well, if I have a current going into a circuit of 5 amps and it reaches a junction, if there's 3 amps on this side, I don't have to measure the other side. I just know that what's left is 2 amps. If I know one, I can guess the other. So, it doesn't get any trickier than that. That's what the junction law means. The other one that we got from him is Kirchhoff's loop law. This one's a little bit trickier, but in a closed loop, if we assign a direction to the flow of current. So I'll show you what this means in just a sec. Assign current direction. Then the sum of the change in potential through the loop will equal 0. All right, so what does that mean? Let's set up a little circuit here so we can look at this. So I'm going to install my power source and I'm going to put a positive and a negative here. The positive is always on the direction of the longest line. So if you're ever wondering, that's how you determine it, and that's why it's drawn the way it is. The longer line is going to be the positive side. Now I'm going to put an object in And I'm going to come around and I'm going to put an object in. And I bet you can tell what's coming. I'm going to come around the corner here and I'm going to put an object in. Oops. I didn't quite make that long enough. So if we ignore the weird little random wire sticking out on the bottom. Now, in science, we know that electricity is the flow of electrons. And that's fine. So we would want to say electrons leave the place where they're all piled up, which would be the negative side, and they flow towards the positive side. That would make sense. Negative things are going to flow away from other negative things and into positive things. However, in the field of electricity, they talked about the idea or the concept of current before they understood what actually was flowing in the current. And so what is typically found for us these days is that the direction of current is defined as away from the positive and toward the negative. So your battery is actually labeled backwards. The positive end of the battery is where all the electrons pile up, and the negative end of the battery is where the positives are that it's trying to flow to. I know that this sucks and is confusing, and I'm sorry, but we need to be able to separate in our mind the convention of how we define flow from what is actually moving inside of these currents. Okay, so when we look at this circuit that I drew, there are 4 different things on it that the current has to flow through. There's going to be potential difference there, here, here, and here. And what Kirchhoff is saying is that if I take V1 plus V2 plus V3 plus potential difference 4, and I add them all together, I'm going to use up all of the energy that was input. So if it was a 12-volt system, 12 volts are going to take off this way, but I'm going to lose a little bit from here to here. I'm going to lose a little bit from here to here. I'm going to lose a little bit from here to here. And by the time that it gets back over here, there isn't going to be anything left. It's going to get all used up. Okay? So the thing that we usually talk about is a battery. Whoops. My stylus quit writing there for a second. Is going to add potential difference. And a resistor and just a sec. My pen is being a bit of a stinker. A resistor is going to take away potential difference. So in the way that we drew our circuit, we would say the positive from the battery is going to get canceled out by the negative from the other 3 objects that are in the circuit. Okay, so that is all there is to Kirchhoff's laws, and they seem simple enough. What we're going to do is work on applying them over and over and over as we study series and parallel circuits. Now, for anybody who actually does like to read about scientists, because it happens sometimes, the guy's name was Gustav, and I usually spell it wrong. Kirchhoff. And I think I spelled it wrong there too, because he has 2 H's in his name. And that's the part that I usually get wrong. So this will help you guys with your notes too. You're not going to be tested on knowing how to spell Kirchhoff, but that's the man. Alright, in this video I also wanted to look at this question. It says, which of these circuits are the same? So in a general sense, take a look at each one. You can hit pause for a minute in the video. That's what I'm going to do. And I'm going to think through the time that it would take to analyze these circuits. Try and write down in your notes which ones you think are the same and which ones aren't the same before you turn the video back on. All right, so I gave myself a second and I thought about what I wanted to say and made sure that I was ready for this next step. So what I want to look at here, I'm going to look just at A for a minute and analyzing A. See if I can make this a little bit bigger. And I can, but now my circle's in the wrong place. That's okay. All right, so here's the battery. If I move out from the battery along the circuit, again, moving in the direction of the longer line, which is positive, I come to a junction where if I turn one way, I get a capacitor, and if I go the other way, I get a resistor. So going back to look at our symbols, we have battery, we have capacitor, and we have resistor. So the energy can either flow through the capacitor or it can flow through the resistor. It can't go through both. Okay? All right, now I'm going to look at B. I'm going to move out along the path here, and I come to a junction where it can either decide to go through the capacitor or through the resistor, but it can't go through both. Well, that's exactly what I had over here. So A and B are the same. All right, let's look at C. In C, here's my battery. I move along from the positive, and no matter what I do, no matter what I do, I'm going to run into that resistor. The resistor is inevitable, and it's going to happen before I get a choice about whether to go through the capacitor or not. So I'm going to go through the resistor no matter what, and I might or might not go through the capacitor. So it's definitely not the same as A and B. All right, so then all we need to do is look at D. So here's my battery. I'm going to flow out from the positive, and right away I reach a choice. If I go left, I can go through a resistor, and if I go right, I can go through a capacitor, but I can't go through both. So that means it's the same as A and B. So A and B and D are all the same. You can choose the resistor path or you can choose the capacitor path, but you can't do both. C is different because you get to do both. Or you can just go through the resistor and go back the way you came and not touch the capacitor at all. All right, so that was kind of a look just to get us used to the idea of the battery, capacitor, resistor, and those junctions, and how to think about following along on a pathway. Now, this is 13 minutes, so this is where I'm going to stop with this video. And the next video, we're actually going to start to take notes on circuits in series.